All right, let's dive into this computer architecture stuff. You gave us these excerpts from William Stallings' textbook.
Computer Organization and Architecture.
10th edition, right. So we're going to try to pull out the good stuff for it.
Yeah, it's pretty dense.
Without, overloading you with too many technical details.
We'll keep it fun.
So Stallings talks about this turning point, late 90s, early 2000s, where compatibility really took center stage. He mentions by 86 dominating in general computing.
Right, and ARM and those little embedded systems.
Yeah, and this kind of led to this whole focus on implicit parallelism. Can you unpack that a bit for us? What did that even mean?
So implicit parallelism, it's like, you know how our computers just keep getting faster? It's kind of like the architecture itself is doing a lot of the heavy lifting.
Yeah.
Instead of relying on super specific instructions, the hardware is finding ways to run multiple tasks at the same time, kind of behind the scenes.
As it's like the computer's figuring out how to multitask on its own.
Exactly. Pretty neat, huh?
Sounds efficient.
Yeah, but Stallings kind of points out some of the limitations here. As technology keeps advancing, it's getting harder to extract that implicit concurrency from programs that were, originally designed for just single core processors.
So it's like trying to squeeze more juice out of an orange that's already been totally squeezed.
That's a great way to put it.
And then there's the whole power consumption issue too, right? I remember reading that some of these superpowered designs just guzzled energy. Not very practical.
Yeah, you think of it like a sports car with a massive engine. Yeah, it's powerful, but man, you're going to be filling up that tank a lot. So that kind of led to this renewed interest in explicit parallelism. That's where the software, it explicitly tells the computer how to run things in parallel.
Gotcha. So instead of the computer trying to figure it out on its own, we're giving it clear instructions on how to multitask.
Yeah.
But that must create compatibility nightmares.
You're exactly right. Stallings talks about the trade-offs that designers have to make. They want to make things faster, more powerful, but they also have to make sure that all the software still works.
Right. Okay, so then Stallings introduces this concept of multi-core computers. He defines it as, a single chip with multiple processors on it.
Yeah, and each one is called a core.
Right, so it's like having a whole team of mini processors all working together.
Exactly, and each of those cores, it's like its own little self-contained unit. It's got its own control unit, ALU registers, and even its own cache, which is basically a smaller, faster memory that sits between the processor and the main memory.
Whoa, hold on, you're going a little fast to me. Cache memory. I feel like I've heard that before, but remind me why it's so important.
So imagine you're working on a project, and you keep needing to refer to this one document.
Okay, I've been there.
Instead of going back to the filing cabinet every time, you just keep a copy right there on your desk, right?
Right, makes sense.
That's kind of what cache memory does. It stores frequently used data from the main memory so the processor can access it super fast.
Oh, okay, so it's all about speed and efficiency.
But
Speaking of speed, Stallings mentions how cache memory design, evolved drastically. In early designs, it only took up maybe 10% of the chip area.
Right.
But now, it could be over half. That's crazy.
Yeah, and all that extra space. A lot of it is dedicated to, making things run even faster.
Like what?
Things like pipelining and parallel execution.
Okay, those sound complicated.
Not really. Well, kinda.
Can you, explain it in a way that my brain can handle?
Okay, so think of an assembly line in a factory. Each worker specializes in one specific task.
Okay.
And the product, it moves down the line as it gets assembled. So pipelining in a processor, it works kind of like that. Different stages of instruction execution, they happen at the same time, kind of like those workers on an assembly line.
Gotcha. So it's breaking down a complex task into smaller chunks that can be done, simultaneously.
Yeah, exactly. And then there's superscalar execution, which is like having multiple assembly lines within a single processor. So it allows instructions that don't depend on each other to be executed in parallel. Really speeds things up.
Wow. So we've got all these cores working together, cache memory speeding things up, and then pipelining and parallel execution making things even more efficient. It seems like we're on the fast track to, super-powered computers. But wait, didn't Stallings mention Amdahl's law? That sounded like kind of a bummer.
You're right. Amdahl's law is it reminds us that there are limits to how much speed up we can get through parallelization.
Okay, so why can't we just keep adding cores and make things infinitely faster?
Well, think of it like baking a cake. Some tasks can be done simultaneously, like mixing the batter and preheating the oven, but some steps have to be done one after another, like pouring the batter into the pan before you bake it.
Oh.
So even with a team of bakers, some parts of the recipe just can't be sped up.
Gotcha. So Amdahl's law is basically saying that there's always going to be a bottleneck, even with tons of cores.
Exactly. It highlights how important software design is. You can have the most amazing hardware in the world, but if the software isn't written to actually use all those cores,
right,
we won't see the full potential of parallel processing.
Makes sense. So it's not just about building faster hardware, it's also about writing smarter software.
Right, it's all connected.
So Stallings mentions that reducing memory access time is like a key factor in performance. He outlines a few techniques to achieve that, right?
He does. He talks about increasing the size and speed of the on-chip cache, which we talked about earlier, as well as increasing the bandwidth between processors and memory. It's like widening the highway so more data can flow freely.
And then there's optimizing I/O handling for those high-throughput devices. It's like having a super efficient loading dock, right?
Yeah, exactly. It's all about making sure data can move around quickly and easily between different parts of the system. We don't want any traffic jams in our computers.
It's pretty amazing how the hardware and software are so interconnected when it comes to performance.
Absolutely. It's like a delicate dance.
A delicate dance, I like that.
Between pushing the limits of what hardware can do and writing software that can actually take advantage of it all. Yeah, a delicate dance is a good way to put it. It really is. Going back through these excerpts, one thing that stood out to me was how Stallings lays out the whole history of computers. Like how we got from those early machines to what we have today.
Yeah, it's pretty mind-blowing when you think about it. From those massive first-generation computers with vacuum tubes to the second generation using transistors.
Yeah.
I mean, can you imagine how much space those early computers took up?
I know, right? It's crazy. And Stallings points out how those transistors were a huge leap forward, making computers smaller and more reliable.
Right.
But then the real game changer, at least according to Stallings, was the third generation when integrated circuits came along. Those systems, like the IBM System 360 and the DEC PDP-8, they were like the rock stars of that era.
Oh yeah, I remember reading about those. The IBM System 360, it introduced this idea of a family of computers, all with the same architecture, but different specs. So customers could upgrade without having to rewrite all their software. That's pretty brilliant.
Totally. It paved the way for the compatibility we have today, which we kind of take for granted.
Yeah, for sure. It's easy to forget how far we've come.
Right. And Stallings doesn't just focus on the big picture. He also gets into the nitty-gritty, like the evolution of the system bus.
The system bus. Refresh my memory on that one.
Okay, so think of it as like the main highway inside your computer. It's how data travels between the CPU, memory, and all the input-output devices.
Okay, I'm picturing it.
And Stallings explains how the width of that data bus, kind of like the number of lanes on a highway, determines how much data can be moved around at once.
So a wider data bus means faster data transfer. Makes sense.
Yeah.
What about, what was it called? The Intel Quick Path Interconnect, QPI.
Oh, yeah, QPI. That's a fascinating one. It's more than just a bus. It's like a point-to-point architecture. So instead of everything sharing one highway, it's like having dedicated express lanes between different components.
So it's like a direct line between departments instead of having everyone crammed in the same hallway.
Exactly. And then there's PCI Express, or PCIe, which is what connects all those peripherals like your graphics card and network adapter to the rest of the system.
Oh, so PCIe is responsible for all those awesome graphics in my video games.
You got it. It's another example of how engineers are always trying to find faster, more efficient ways to move data around.
Yeah, it seems like speed is the name of the game.
It really is. And speaking of speed, remember cache memory?
Oh yeah, we touched on that earlier.
Well, Stallings dedicates a whole chapter to it, and for good reason. It's a crucial component when it comes to performance.
Okay, remind me why it's so important again.
So cache memory takes advantage of this principle called locality. Basically, it means that if your computer accesses a certain piece of data, it's likely to need other data that's stored nearby.
So cache memory is like a mind reader, anticipating what the processor needs next.
Uh-huh, you could say that. It basically fetches those nearby chunks of data from the main memory and keeps them readily available in the cache, so the processor doesn't have to wait around.
It's like having a super organized assistant who always has the right file ready before you even ask for it. And Stallings talks about different ways to organize and retrieve data within the cache, like direct mapping, associative mapping, and set associative mapping.
Right, and each technique has its pros and cons. It's all a trade-off.
Makes sense. What about when the cache gets full? How does the computer decide what to keep and what to get rid of?
That's where cache replacement algorithms come in. They determine which pieces of data or cache lines get evicted to make room for new stuff.
That's pretty clever.
And there are a bunch of different algorithms out there, each with its own logic.
It's amazing how much thought goes into something as seemingly simple as cache memory.
I know, right? It's all about maximizing performance, but just to bring it back, why is cache memory so important in the grand scheme of things?
Well, it sounds like cache memory is kind of the unsung hero of computer speed, constantly working behind the scenes to make sure the processor has instant access to the data it needs.
You nailed it. It's like the processor's pit crew, keeping everything running smoothly.
I like that analogy.
So we've talked about how computers have evolved over time, how the different components are connected, and how cache memory keeps things running smoothly.
It's been quite a journey, and I feel like we're just getting started.
We are. There's a whole universe of cool stuff still to explore.
Okay, so we've talked about the hardware, the nuts and bolts, the chips and the circuits, but now let's switch gears and talk about the software side of things. I'm guessing this is where things get really exciting for you, right?
Absolutely. This is where it all comes together. You know, all those intricate hardware designs we've been discussing. They're ultimately there to serve the needs of software, the programs that we use every day.
Makes sense. And Stallings, he dedicates a good chunk of his book to this whole concept of the operating system, the OS. He describes it as, the software that manages all the computer's resources and acts as a mediator between programs and the hardware, kind of like the conductor of an orchestra.
That's a perfect analogy. The OS is like the unsung hero handling all this stuff behind the scenes, memory management, process scheduling, file systems, you name it.
Yeah, without it, our computers would be a total mess.
You would be chaos.
So it's like the ultimate multitasker, juggling all these complex operations. I can barely keep track of my to-do list.
Well, the OS has some pretty clever tricks up its sleeve. Stallings talks about multi-programming and time sharing, which help create this illusion that everything is running smoothly at the same time.
Oh yeah, I remember those. Multi-programming is like having multiple programs loaded into memory at once. Right? So even if one program is waiting for something, like data from the hard drive, other programs can still keep running.
Exactly. And time sharing, it takes that concept a step further by giving each user a little slice of processor time. So multiple people can use the same computer, and it feels like they each have the whole system to themselves.
It's kind of like magic, how the OS creates this sense of abundance, even when resources are limited. But I bet memory management is one of the biggest challenges for an operating system.
Oh yeah, for sure. And Stallings gets into all these different techniques like swapping, partitioning, and paging. Paging is the one that always blows my mind.
Me too. Remind me how that works again.
Imagine you have this giant jigsaw puzzle.
Okay.
But your table is too small to hold all the pieces at once. Paging is like breaking that puzzle down into smaller sections that you can swap in and out of the table as needed.
So it's like having an expandable puzzle table. That's pretty brilliant. But how does the computer keep track of all those pieces?
Well, the OS uses these things called page tables, which are like a map between the virtual addresses used by programs and the actual physical locations in memory. It's complicated, but super efficient.
It's amazing how much goes on behind the scenes to make computers do what they do. It's like a whole hidden world.
Right. From the hardware to the software, it's a real testament to human ingenuity. We've come a long way from those room-sized computers to the powerful machines we have today.
And Stallings does such a great job of breaking it all down, making it understandable.
He really does. He gives us the tools to understand not just what computers do, but how they actually do it.
Well, we've covered a lot of ground in this deep dive. The evolution of computer architecture, how processors and memory systems work, and even how operating systems keep everything running smoothly.
Yeah, it's been quite a journey. And the amazing thing is, we've only just scratched the surface.
That's the beauty of it, right? The more you learn, the more you realize there's so much more to discover. We hope this deep dive has, sparked your curiosity and inspired you to keep learning about this amazing field.
Absolutely. Maybe you'll even be inspired to pick up Stallings' book and continue the journey.
Yeah, why not? And until next time, happy exploring.